that leads directly into our next section, which is the core, right? So one of the faculty members from the chemical engineering department, Carl Laird, is going to step in now and really talk specifically about the core and how you're going to build these foundational skills. And then the next section will go into how they intersect with your discipline. So hopefully that will give you a sense of where we're going. Carl, are you ready?
I am ready, if you can hear me okay. So thank you very much, Jennifer and David and Shelley for the lead in there. I'm happy to take this opportunity to speak with you folks. So this slide is really illustrating a fundamental concept that went through the design of this program. This program was really designed to provide the graduates with the opportunity to find a unique career, but not one that's only ML, not one that's only engineering, but one that is essentially the intersection of those two. And so what you will see in these programs, there is a component of the program that is the same across all of the different departments in engineering that are involved in the program. And there's part of the program that is specific to the domain of your interest, if you're a chemical engineering student or a civil engineering student, et cetera. And so 42 units, this is CMU's version of credits. You can divide by 3 to do the math. 42 units, roughly 1/3 of the curriculum is in the core AI engineering. And the remaining 2/3 of the curriculum are inside the discipline and focused on discipline-specific coursework. Now, it's no secret that industry and research endeavors have really seen tremendous value in machine learning and AI. And many engineering companies for the past decade have tried to realize this benefit by hiring people specifically trained in machine learning and sitting them next to people specifically trained in engineering. And what we've been hearing from companies is that that hasn't been nearly as effective as them being able to hire students that have a background in an engineering discipline as well as machine learning so that they can speak the language and cross the boundaries of both of those capabilities. So this is something that's sought after from our industrial counterparts that look to hire our students. So I'm going to talk a little bit more about these specific core courses. Now, I served on the MSAIE task force that focused on the design of these courses. And the fundamental philosophy behind designing these courses was really about 3 pillars. It was about making sure we had coursework that could serve consumers. These are those who use, analyze AI machine learning tools for domain-specific applications. And here, the focus is really on a broad understanding of the capabilities of AI across that spectrum. The second pillar is producers, those who are looking to actually develop new tools that go beyond treating these machine learning capabilities as simply black box, download PyTorch and use PyTorch. Those who kind of want to go beyond that and tailor or align these tools with particular applications or existing physical models. So the education is really focused on a deeper understanding of what's under the hood for these tools. And the last is enablers. These are groups of people who develop the infrastructure that is needed for us to realize AI engineering in the real world. This includes cloud resources, networking, data distribution, et cetera. And it's these 3 pillars, the consumers, the producers, and the enablers, that really form the foundation of designing these courses. Let me go through these 4 courses in a bit more detail. So the first is Systems and Tool Chains for AI Engineers. And this course is focused on teaching students to be effective users and developers of AI systems, the workflows, the software tool chains. Students are going to gain hands-on experience with a variety of different computational tools necessary to process real-world data sets, and do that under conditions that require real engineering design choices. They're also going to gain experience with a variety of different hardware platforms, including CPUs, GPUs, and other accelerators as appropriate. They're going to basically focus on the principles and key trade-offs that are involved in data collection, storage, data engineering, neural network engineering, framework architecture, and how do you build these systems and make them effective when there's constraints on resources, data, et cetera. Next slide, please, Jennifer. So this is really the bedrock of the program, the Introduction to Machine Learning for Engineers. This course introduces students to the fundamental methods and algorithms that are at the core of modern machine learning. It covers the theoretical foundations, but also practical techniques for both supervised and unsupervised learning. It includes a large number of hands-on assignments, in addition to a larger course project aimed at strengthening your problem-solving techniques in engineering using these machine learning tools. Some of the topics that are covered are probability and Bayesian learning, classification methods, neural networks, support vector machines, and a number of the other keywords that you know are important in the machine learning community. The third course, which is taught in the spring semester, is the Introduction to Deep Learning for Engineers. And this, although it's called an introduction, is really taking a more detailed dive into the methods and applications specifically for deep neural networks and how they apply to different tasks in engineering. So students will combine their domain knowledge in engineering with artificial neural networks and gain a stronger understanding of some of the more advanced topics associated with deep learning and its uses. This is going to cover techniques like convolutional neural networks, adversarial networks, graph neural networks, some of the really more fine-grained techniques that are used in machine learning. And the fourth core course is on trustworthy and ethical AI engineering. And this course is really designed to ensure that CMU AI engineering students graduate with an awareness of the challenges associated with ensuring the AI tools that we developed are trustworthy and ethical. The goal is to make sure that you, the students, have a precise understanding of different threats and concerns when deploying AI solutions in the real world, and also to help you focus on really what are the end-to-end deployment challenges, societal issues, and policy challenges that face the development of some of these tools and the deployment of some of these tools. So this course is going to provide exposure to the best practices for avoiding and handling these concerns when we actually deploy these techniques. So collectively, these four pieces, these four courses, the Trustworthy and Ethical AI course, the Introduction to Machine Learning, as well as the more advanced Deep Learning course, and the Systems and Tool Chains course, these are really set out there to meet this philosophy of providing an effective education for students. And we really capture these specifically to make sure that we could expand the scope of opportunities that were available for students graduating from this program. So not just users of the tools, but also students that understood what was going on under the hood and could tailor these tools for individual engineering tasks. Jennifer, back to you. Thanks.
Awesome. Thank you so much. We're running so smoothly that we're a little bit ahead of time. So there is a question in the chat. Again, remember everyone on this call, I am an admission, so I do not know any of the technical words that Carl just said, but this question that popped up, do you equip students with skills in all spheres of machine learning, supervised, unsupervised, reinforcement, machine learning, neural networks, especially, or students who choose where to concentrate? Is that something you can sort of address as we're leading into the next section where we're going to be talking about the more discipline focused information?
Yeah, let me say a few comments about this, Jennifer, because I think this is a good question. So our Introduction to Machine Learning for Engineers course is really designed to be broad and to cover a lot of these aspects. So supervised and unsupervised learning is taught there, neural networks, and as I mentioned, even some of the more fundamental methods, support vector machines, et cetera. This is all covered in that broad overview course. And the opportunities for students to, once they're exposed to that broad overview, to learn more about some of the individual pieces and dive deeper is through electives that are available inside each of the individual programs, and also through project work. Some of the departments have a specific research component where students are taking what they learn in these ML courses and applying them to actual engineering research problems. And other disciplines are focused on having project courses that really teach students how to do that integration. But this core piece, it's really clear that it is common across the engineering disciplines. So all of the students graduating out of this program, whether they come out of chemical engineering, civil engineering, electrical engineering, they have that same foundational core, that broad exposure to all of these topics to make sure that they're aware of all of these different techniques in machine learning. So there's opportunity we provide the broad overview, and then there's opportunities for students to fine tune and dive deeper in the areas they're particularly interested in.
Awesome, awesome. I think that's the perfect segue to our next section, which we are calling distinctions by discipline. And I'm actually going to stop sharing my screen, actually there, so we can see all the amazing people here. Oh my goodness, I just love it. Thank you to everybody. You can see that this is a true team effort and very interdisciplinary. Really the first time the College of Engineering has really done anything like this. And so it's just really been a pleasure to work across all of the disciplines. So what we're going to do now is ask a representative from each of the departments that is involved in these programs and has their own unique program to spend 1 or 2 minutes talking about a distinction in their program, a really interesting or cool story or anecdote that will help you kind of see where the intersection between that particular discipline and this program lie. And we want to tell you this because eventually at the end, we're going to ask you to apply, right? You're thinking about applying, and hopefully this will help you determine where the best department or which program is the best department for you. I will just say on the side, I have seen lots of questions about application deadlines and fees and funding and all of those things. And I promise we're going to get to those topics at the end. So we're going to start off with one of the faculty members in the biomedical engineering department saying, would you mind going first? And we're going to go alphabetically through the other departments and we'll see how that goes. Thanks so much.
Thank you, Jennifer. Hello, everyone. My name is Dr. Sang Shiva. I am the faculty member of the biomedical engineering department. So let me quickly share with you some examples how we can integrate machine learning and artificial intelligence in biomedical engineering. So if you choose to go with this degree with the flavor of biomedical engineering, you actually have the ability to choose your focus on, let's say, you want to know how be able to apply machine learning and AI in tissue engineering, in bioinformatics, in bioimaging. So in this particular example, let me just focus on the bioimaging part. So let's say a person were to have concussion or has some condition that can cause fluid that built up in the brain, and this can actually cause growing pressure inside the skull that can lead to headache. This increased pressure can injure the brain and or the spinal cord. So the earlier we can detect this increase in pressure, the earlier we can actually provide appropriate intervention. But currently, to actually measure the intracranial pressure, the doctor actually has to drill through the skull, which is not exactly practical, right? So in our department, Dr. Kainer Stauffer, she's one of the faculty members, and her group actually explore whether they can use an optical imaging device to predict the intracranial pressure. This device can measure the brain blood flow signal by shining the light through the skin and tissues and measure the reflected light. Her group then developed a machine learning algorithms that can extract features from the blood flow and identify the features that are the most predictive of the intracranial pressure. Turns out that the most predictive feature of the blood flow waveform is actually the most prominent feature, which is the peak height. So what does that mean? It means that we can now go back and redesign the optical imaging device that can be very simplistic, sort of like a smartwatch, but for the forehead, just like be there. But with the embedded machine learning model for intracranial pressure prediction. So now we'll be able to measure, to monitor the intracranial pressure in patients continuously, but without any drilling anymore. So someone with both machine learning and AI training with the domain knowledge in the biomedical engineering field will be able to tackle this type of healthcare challenges. Thank you.
Wow, that sounds interesting to me. Thank you so much. That was really wonderful. We're going to move on to civil and environmental engineering. Professor Burgess, I apologize if I pronounced that wrong.
No, perfectly fine. Hi, my name is Mario Burgess. I'm a professor in the Civil and Environmental Engineering Department, also with courtesy appointment in Electrical and Computer Engineering. So I'm asked to give a distinction for civil and environmental engineering. Civil and environmental engineering is very broad, and there's a bunch of different application areas that one can concentrate on. So I'm going to pick on one particular one close to my heart, but also the one that is going to be focused on in this first year of the program. So we have a capstone course, or a course that is sort of intended to be integrative of all the things that you will learn through the masters and you take at the end. And in this particular case, the course that we're suggesting for this first year is a course on autonomous and sustainable buildings. And so I had to make the pause originally to say, like, we are very broad. Civil engineering covers everything that supports urban modern life, anywhere from water sanitation all the way to traffic engineering and structures. The particular case of buildings, which we civil engineers design and operate, where machine learning comes in and AI comes in is during the operations in particular. It's also in other areas, but in the operations, it's currently a very hot topic in the industry. And the reason is that to make buildings much more efficient in their operation and much more comfortable, there are trillions of decisions that need to be made. And those decisions are typically made by rules of thumb right now, because they are so many, or by manual effort, which is costly. So I'll give the specific example of things that we do in this particular course that may be attractive to some of you. Say we take the specific way that a room is being controlled for providing heat and ventilation, or cooling and ventilation to that room, which in the case of campus buildings is typically on a schedule that is rule-based, and it says you keep the set point at 72 degrees Fahrenheit during the occupied hours, which we assume to be 8 to 5. And then after the occupied hours, you relax that set point and either bring it down during the wintertime or bring it up during the summertime. And that's kind of the rule that we have. And we think, okay, so how can machine learning help us do a better job there? Or how can AI help us do a better job? And in that course in particular, we cover all the elements of the domain expertise that are required, thinking about the thermodynamics of the room, how it actually reacts to changes in temperature outside, understanding human comfort and thermal sensations of comfort, and so on and so forth. And then think about the equipment that we have in hand to provide an AI with information about what is really happening, the sensors, the schedules, the virtual interfaces to the class reservations and things like that, and then design algorithmic solutions that take all that data and learn how to optimize, knowing how the building should behave in order to become more efficient. And so I'm just scratching the surface there. There are a bunch of different techniques that we use under the hood, anywhere from traditional supervised learning all the way to deep reinforcement learning. But that's the idea, that there are specific problems in the civil engineering world, in this case, autonomous buildings, that require that we make decisions much faster, and AI is sort of our helper there. And we learn how to train AI algorithms to do that.
Awesome. Thank you. That's again, I'm going to say everything's interesting, so I won't say that every time, but thank you so much. And there are a couple questions directly for you, so we will hold them till the end, and there's plenty of time during this section to answer some questions, so we'll definitely come back. We are going to move on to chemical engineering right now and ask Professor Kitchen to take the next example.
All right, great. So in chemical engineering, there's a lot of ways that we use machine learning as well. I want to focus on the slide here, which is using what we call large machine learning AI catalyst models in chemical engineering. So a lot of what we do is focused on how do we design catalysts for reactions. For example, in a car, there's something called a catalytic converter that converts CO and NOx and SOx into less environmentally damaging materials. And people are very interested in making catalysts to produce hydrogen from water, to produce fuels from CO2, for selective chemistries, et cetera. And the way we've done this for many decades now is we can simulate things like you see down here. We can make a model of a surface. These different balls are say blue is palladium, gray is silver, and this is an ethylene glycol molecule wiggling around on the surface. So we can build these models and use quantum chemistry calculations to say what happens, but these are pretty expensive. It can take weeks to do one calculation. And if you're trying to find a new catalyst, you probably need to look at hundreds of possible things, or thousands. And so this project that I'm describing, the Open Catalyst Project, is one where we can run, say, millions of these quantum chemical calculations and build machine learning models that are capable of going across all different kinds of materials, metals, oxides, nitrides, ionic compounds, 2D materials like graphene or MXenes, and calculate properties and reactions that happen on them. And that allows us to do things where it's not possible with quantum chemistry because it's too expensive, but we can discover new materials for CO2 utilization, for fuel cells. We can do accelerated simulations up here. We can look at a broader range of chemistry. And so that's one way we've been using machine learning in chemical engineering for accelerating molecular simulations for understanding chemical systems.
Thank you so much. We are going to move on to the Department of Electrical and Computer Engineering, and I'm going to ask Professor Gibbons to go next. Thank you.
Yes, thank you. Yeah, I'm Phil Gibbons, professor in ECE. So the thing about ECE is that we actually have components that address not just the use of AI, but actually the development of the mathematical foundations and the systems in support of AI. We like to think of those three categories as the enablers that are producing the systems enable things, the producers that are coming up with the new machine learning algorithms and optimizations algorithms and so forth, and the consumers, which are all the great uses of AI that we've seen even across all the other departments as well. And so it's sort of an opportunity there to develop. If you're interested more of a computer software person, you're interested in computer systems. We have offerings that would be part of this program to help you develop expertise in those kind of systems, in particular systems that target making machine learning and AI much more performant, particularly at large scales. In terms of the producers, we have a whole series of courses on that are math heavy for most of them. So if that's not your cup of tea, then maybe these aren't your favorite courses. But if you are a math whiz to some extent, then we have 5 or 6 courses that could be made part of this program, of your program, that address new ways of optimizations, new algorithms for based on machine learning and AI. And then at the consumer side, we have classes like autonomous driving class. You can learn, end-to-end all the aspects that go into the development of self-driving cars from the systems and software perspective. And so you go through the whole pipeline of that. We also have courses that look at things like speech understanding and recognition and various others. So I will leave it at that.
Yikes. Thank you so much. That's really great and very comprehensive. We are going to now go to the Information Networking Institute and my colleague, Dr. Hanan Hipshi.
Thank you, Jennifer. I'm Hanan Hipshi. I'm a faculty at the Information Networking Institute. I majorly teach security courses. So AI and cybersecurity are really very interesting two fields. They're on the news all the time. And often it's the time where it's often that you see degrees that either focus on security or focus on AI, but then how would the two talk together? And I think that's why we were excited about this new degree. You will get to take security classes where you will be sitting in a security class, learning security deep enough, just like everybody else who's taking a security class, and you're also going to be taking the other AI core requirements. But then there are classes also in the program that would help you combine the two together and look deeper into that picture. Examples of that are around us a lot if you start thinking about them. For example, we're all now seeing systems that use facial recognition. But if you think about it from an attacker perspective, those AI systems can be attacked. We can have fake pictures, and with the use of AI, we can impersonate someone and then authenticate on their behalf. You just listened to biomedical engineering, which is doing great progress in algorithms to help with medical imaging and analyzing disease. Now, once we start deploying these systems, you worry about those kind of attacks that could cause misdiagnosis. So how would we handle that, and how we keep the ethics also part of that process? I don't mean to scare you, so let me talk about the defensive side. Since there are lots of security is a very big field, and we have things where we want to protect systems, but it becomes very tedious for the human analyst. We figured maybe we can use the AI models to analyze the data and the logs and all those information we collect from sensors or networks, so we can ease the process and help humans think smarter. One reason why your spam filter in your Gmail is working better at detecting spam is because we are using AI technology and machine learning in there. So it's around us more than you think, and this program will help you connect the dots. And I went 30 seconds above the 2 minutes, Jennifer, sorry.
Sorry, I couldn't find my mute, so you had an extra 30 seconds. Thank you, Hanan. That's awesome. We're going to jump into materials science and engineering next with Professor Robert Hurt.
Hi, I'm Professor Robert Hurt at Material Science and Engineering. I'm going to build a little bit on what Professor Kitchen started with there with the catalyst. So machine learning in material science and computer vision in material science, and these AI programs are really helping material scientists develop new materials and look at all the chemical reactions and well, we have somebody in there. So
continue, sir.
Oh, I think Professor Hurd, you have to unmute yourself now. I think we're good.
Okay. Are we good to go? Okay. So in material science, we are using really the two sides of AI. For the machine learning side, we are exploring, of course, different combinations of chemical reactions similar to what was presented by Professor Kitchen. But you can also apply this to a lot of systems, such as battery systems, development of new technologies, new batteries, for future energy uses and things like this. So this whole machine learning side is really working on developing this complete new area of materials. So if you've done material science as a background, you know it's very time-consuming, experimentalist focused matters, and this new AI programs help us accelerate this. The other side of the engineering part of materials is in, of course, the process automation and controls of processes. Certainly computer vision in additive manufacturing and production processes has helped optimize those and not only optimize from an efficiency standpoint, but also from a quality standpoint. So we are looking also at implementation of AI in these environments as well. So we'll see manufacturing of the future, the 4.0 manufacturing environment, certainly involve AI throughout wherever materials are being used, manufactured, and processed. So in our graduates are kind of looking at a couple different avenues of employment. Typically are finding national labs where there's rapid technology development in materials, startup ventures who are looking to find faster and more efficient processing to compete against the existing companies in manufacturing, and a lot of consulting companies who are consulting directly to the large manufacturers on how to improve the optimization of their processes. So these kind of things are what you might find yourself doing with material science.
Thank you so much. And last, but certainly not least, we're going to have Professor Amir Farahmani from the Mechanical Engineering Department.
Hello, everyone. This is Amir. I'm a professor in mechanical engineering. So I'm going to talk about how we can use AI in mechanical engineering and what are some of the job perspectives, some of the exciting things that we can talk about. So essentially, the way that I see it is that we can use AI in a lot of different areas of mechanical engineering, considering for the phenomena that really are complex and we don't have any mathematical model, where we don't know the physics, of a process, and we wanted to engineer and predict because, engineering is all about prediction. And we wanted to, for the cases that, computational fluid dynamics or finite element methods are very slow, we wanted to speed up the process. So we built really fast surrogate models. And for the places that in all of the experimental areas of mechanical engineering that we have abundance of data, but we wanted also to make a precise model. So it can span over fluid mechanics, solid mechanics, bioengineering, material science, dynamic and control and manufacturing. For example, one of the areas, as you can see, is like, for example, can we use vision to predict the dynamical motion of a jellyfish in an aquarium? Or in robotics, for example, complex robotic manipulation tasks can be used deep reinforcement learning or reinforcement learning. For turbulence, that we don't have really accurate models. All of them are empirical. Can we use AI to build the predictive models that are fast? Or for example, for computational fluid dynamics and particle dynamics, how can we accelerate them? In additive manufacturing, this is a process which is very slow, but you can print or you can manufacture very difficult parts, or complex parts. But it's very slow. Can we speed it up using AI by process monitoring and control? We can do material property prediction that John Kitchen and Robert actually talked about it by predicting their properties because doing experiment or density functional theory calculation is very, very expensive, but you can speed it up. Or build reduced order model for CFD or finite element models using AI. So the areas that essentially you can do, you can do a lot of cool stuff. So, with the PDE discovery, in engineering, we solve a lot of PDEs. For example, you have this pendulum that is moving, what is the equation of motion of that? Or you can see, for example, the tree is moving, the branches of tree. Can we find the equation of motion of that tree using AI and vision? For material discovery, can we like high level in additive manufacturing, there are this thermal management and there's an interplay between, multi-phase flow, turbulence, and all these complex phenomena that are simultaneously going on. How can we learn based on the data that we have and predict the flaws, defects that are created? And then finally, accelerated scientific computing, how we can accelerate prediction of, for example, the fluid that is moving inside a vessel. So, for example, you wanted to handle with robotic manipulation a kind of like cup of coffee. So how can you actually plan it, not to spill it? So there are a lot of different areas that you can use AI and machine learning. And in this program, actually, we equip you with teaching, the core courses that are required with these type of phenomena and all the assignments, and, everything is geared toward that. Yeah.
Wonderful. Thank you so much. Wow, I think that is really, in my opinion, at least, highlights the really unique components and aspects of all of our programs. Amir, I don't know if you want to take your slides down. Yep, yeah, thank you. Perfect. So we do have about 10 minutes left, and I am going to rely on some of my colleagues to draw out any kind of overarching questions that came in the chat. There were many. We may not address all of them, but we will definitely be sharing the slides for today and the recordings. And honestly, at a very high level, many of these questions will need to be addressed by the individual departments that you're applying to. So we want to speak to some themes today and help you sort of identify the department that most aligns, the department or departments that most align with your interests and get you in the right place. Melissa, are there any questions that you noticed that might be good to go to next?
Yeah, I did. So I just put a quick answer in for a recent question about the fall semester batch, like who was the first cohort. There were a couple questions about the ability to complete a dual master's degree. So for example, doing like an MS in mechanical engineering plus an MS in AI engineering. So I don't know if we want to address how the MSAIE engineering curriculum is combined with department curriculums.
That would be great. We are going to get into a little bit more about admissions later, but I think this is a perfect question with all the departments because I know there are some nuances depending on the duration and the research. So I'm happy to let the faculty from various departments raise your hand or feel free to jump in and answer that question. Anyone want to go first? I think that to be more clear about the question, I think sort of how this master's degree would work for somebody who wanted to continue on to a PhD and potentially complete that. Is it possible? Is it encouraged? Those types of things, if I'm understanding correctly.
I think the easy answer is yes. But like it with any other master's degree, at least in our case in civil, we would encourage the specific student to explore opportunities for research through their program. There may be some there's additional units that can be used for, say, independent study or things like that allow the student to explore that. Because if you want to go into PhD later, it's best to use the time that you're here to think about what you would be doing in a PhD. The program prepares you well on the technical part, but then it's the research component that needs to be added.
Awesome. And again, we'll be sharing more information about this moving forward, but many, I'd say at least 50% or more of the programs have the ability to do research. And honestly, at the foundation of Carnegie Mellon, we are an interdisciplinary research institution. So there's no lack of research happening here for our students. Professor Laird, do you want to jump in?
Yeah, let me just add, I was going to say some of the same things that you said already, Jennifer, right? Carnegie Mellon is heavily focused on research. And so preparation for students wanting to go into the PhD program is part of what we do, right? The other thing that I will add is many of these questions. So the core piece, the core courses that is part of the MSAIE that is the same across all departments, we focused a lot on that part because it's the same across all the departments. Some of the questions that students are asking will be a little bit different depending on the specific department program. So each department has tailored this a little bit to do what they think is best within their domain. And so I would just encourage students to reach out to the program specific to the departments that they're interested in as well, and make sure that they can get some specific questions answered there. For instance, the Chemie program has a research component that the students take. You know, you mentioned, Jennifer, about half do, and so those are questions that might be specific to a particular discipline.
Yes, and I think that on that note, I will jump back into the presentation so that we can finish it up and then go from there. Oh, go ahead,
Sorry.
Melissa.
So sorry. There was just one more really good question I think I just want to call attention to. And the question was what the difference is between the MSAI engineering program offered by the College of Engineering and what the difference would be in pursuing an AI or a machine learning program in the School of Computer Science.
Whoa, I missed that one. That is the question. That is the question. I don't know if anyone wants to tackle that one.
I may be answering too many of these, Jennifer, so I'll let other people chime in too if they want to add. But I think it's that key slide that you showed that is integrating the AI background with the actual engineering discipline and domain. So it's not just I got an engineering degree and then I got an AI degree. This program is really ensuring that students are able to integrate those two. Whereas if you did your AI degree specifically in a computer science department, either at CMU or elsewhere, that would have a very different focus solely on the machine learning and AI. And so that domain specific part, I think, is really unique to this engineering program. Now, the second thing that I think is really critical is our program is geared towards students who have an engineering background. And that may be different than a student that has a computer science background. And so we have organized the coursework and preliminary material, et cetera, to make sure that we're bringing students with an engineering background up to speed to succeed in AI.
And the thing that I would add from my admissions lens and perspective that I would talk to students about is as an engineer, we tackle problems. We engineers tackle problems from a different perspective, sometimes coming at them from various angles. And I really believe the intention for this program is to tackle this question of AI from an engineering lens and an engineering perspective. So again, I saw some questions in the chat that were very, very specific to even the labeling of our program. So you will see us talk about MSAIE as an entity, and that refers to sort of the fact that all 7 of our departments are offering these programs, but in reality, they serve as individual programs.